This presentation deals with a special class of non-Newtonian fluids known as Boger fluids. As we shall see, they were named after Professor David Boger, who first brought them to the attention of rheologists. In recent years, these liquids have had a massive influence on research in non-Newtonian fluid mechanics. Boger fluids usually consist of very dilute solutions of high molecular weight polymers in relatively viscous Newtonian solvents. They are characterized above all else by a constant viscosity over a reasonable range of shear rates, whilst at the same time being highly elastic. It is now over 25 years since Boger fluids were first introduced, and it seemed appropriate to recognize their importance and influence by dedicating one of the University of Wales films to their history, makeup, rheometry, behavior in complex flows, and theoretical modeling. So let us first ask the question, when and how did these Boger fluids first receive notoriety? Let David Boger himself provide the answer.
In 1965, after completing a PhD at the University of Illinois in the USA, I rather rashly decided to leave the US and take up a 3-year appointment in the then newly established Department of Chemical Engineering at Monash University in Clayton, which is now a suburb of the greater city of Melbourne in Australia. I think many people thought I was mad, particularly my parents, as the job market in the USA at that time had never been better for chemical engineers. I arrived at Monash in December of that year thinking that I would continue my PhD research in heat transfer. At this time, I knew nothing about rheology and or non-Newtonian fluid mechanics. As would be the case, I was encouraged to move in this direction by the then Professor O.E. Potter. What vision he had. My first research student was A.V. Rama Murthy. We made lots of mistakes, and it really was a case of the blind leading the blind. But we ultimately got to the stage where we could measure the first normal stress difference, viscosity as a function of shear rate, and slowly got to the stage where we could measure dynamic properties as well. Rama Murthy and I then looked at entry flow for viscoelastic polymer solutions, and we got very, very confused between inertia, relatively high Reynolds number flows, shear thinning effects, and or the lack of elasticity in fluids. We thought perhaps that our carboxymethylcellulose solutions were inelastic and our polyacrylamide solutions were viscoelastic. We didn't understand the relative time scales associated with the process versus a relaxation time associated with materials, even though the concept of a Deborah number had been established by that time. The next student whose work really led to the development of Boger fluids was the late Peter Cable. Cable published 3 papers in the ICHE journal which really represent a remarkable piece of work, looking at the vortex formed in the corner of a 4-to-1 contraction. He presented velocity profile data, measured the hard way using streak photography, and looked at the instability problem associated with the flow. A beautiful piece of work which has never received the recognition that perhaps it should. We did realize from the work, however, that there were lots of variables in this investigation which we weren't controlling. For example, we got confused again between low and high Reynolds number flow. That is, the flow with and without inertia. We got confused by shear thinning, and of course we weren't able to isolate elastic effects in flows. At that time, which was in the early 70s, there was a lot of talk about drag reduction, and at that time I don't believe it was a commercial reality. Because we didn't know anything about viscoelastic fluid mechanics, I naively believed that turbulent drag reduction was due to the influence of fluid elasticity. As it turned out, many years later, this in fact is true. But we also knew that we were unable to measure elasticity in a water-like fluid, So again, naively, I thought that if we were able to put the same big molecule in a viscous Newtonian fluid, we could up all the stress levels and hence we would see elasticity. Well, in fact, that turned out to be true. Rod Brinnington made up the solution, first dissolving a small amount of polyacrylamide in water and then using a commercially available corn syrup. Off he went to a rheogoniometer and measured the first normal stress difference and the shear stress as a function of shear rate. I very well remember when he came up the stairs to my office and presented the linear shear stress shear rate data and the first normal stress data, which went from quadratic behavior at low shear rates to non-quadratic behavior as the shear rate increased. Lo and behold, what we had was a constant viscosity, highly elastic liquid with a low shear rate Maxwell relaxation time of the order of a second. We then started to look around to see if there were other materials that exhibited similar characteristics, and as it turned out, the polymethylsiloxanes, I believe they were dark Horning fluids at that time, also exhibited quadratic normal stress behavior and a shear stress that varied linearly with shear rate. The difference, however, between these materials and the corn syrup-based original Boger fluids is that the elasticity level was very low. The first paper announcing the unique characteristics of high elasticity with constant viscosity was published in 1977 in the Journal of Non-Newtonian Fluid Mechanics. I well remember going to the University of Delaware on study leave in 1976, being concerned as to how good our measurements were and wondering whether we were in fact measuring what we thought we were measuring. So I made arrangements for a sample of material prepared at Monash, with the properties measured at Monash by Binnington, to be sent to the University of Delaware, where one or more Den's students was asked to make similar measurements. He did, and the results agreed. 12,000 miles separation, 2 hemispheres, and we got the same results. It was after this agreement that the 1977 paper was published. The naming of these materials, Boger fluids, of course was done by Ken Walters at what to me was the most exciting meeting to date in non-Newtonian fluid mechanics, where 90 of the world's best in the field of non-Newtonian fluid mechanics spent a week together at the Catholic University of Louvain-la-Neuve from 28th of August to 1 September 1978, a meeting organized by Marcel Crochet. Herein Ken's general lecture entitled Developments in Non-Newtonian Fluid Mechanics, published in the Journal of Non-Newtonian Fluid Mechanics, Volume 5, April 1979, he bemoaned the fate of simple constitutive equations at that time in that none of them represented reality, in the sense that a Maxwell fluid or, moving up the hierarchy, an Oldroyd B model were really for constant viscosity elastic liquids. He followed on by saying that the discovery of Boger constant viscosity highly elastic liquid has recently given renewed hope in this direction, at least for a small subset of really elastic liquids, with the side effect that some of the early analysis for simple fluid models may not be as obsolete as their dating would suggest. As we now know, even though such constant viscosity elastic liquids have what appear to be very simple characteristics, their elongational behavior is dramatic in how strain thickening it is, and indeed, this sort of extreme strain thickening behavior has undoubtedly caused some significant problems in terms of being able to model their behavior. Be that as it may, at the same conference we presented the first of a significant number of papers on various aspects of entry flow of constant viscosity elastic materials. The paper with H. Noyen, entitled The Kinematics and Stability of Die-Entry Flows, presented the classical photograph reproduced here, which has since cost international granting agencies huge resources. It demonstrated the growth of a corner vortex and the onset of an instability in the flow, not dissimilar to that observed by some melt polymers in extrusion. Although today numerical simulation can predict vortex growth, no one has yet been successful in predicting the increased pressure drop as a function of elasticity in such flows. The vortex growth phenomena is now known as vortex enhancement. After this original work, there were a large number of papers on various flows looking at elasticity in isolation, jets, spheres, drop breakup, etc. Following on from our earlier work was the development of a second Boger fluid by Tam Schroeder and co-workers, who produced the first organic-based fluid, which was the polyisobutylene polybutene fluid. They also suggested that the Oldroyd constitutive equation might be a good model for such fluids. Today at the University of Melbourne, our own work continues on these sorts of materials, having now moved from high viscosity materials like those developed in the original corn syrup water system and the polyisobutylene system to the more recent polystyrene system to low viscosity materials, where exciting work is being continued on drop formation, drop impact, atomization, etc. We didn't expect the name to live on, but today I'm told that if you go to the web, you will get between 200 and 300 hits if you search for Boger fluids. There certainly have been a lot of papers that refer to such materials in all kinds of situations. The work continues on such materials, and the book, Rheological Phenomena in Focus, presents many photographs which illustrate the influence of elasticity in the absence of many other effects related to shear thinning and/or inertia. Who would have ever believed that an American migrating to Australia, who knew nothing about non-Newtonian fluid mechanics or rheology, would have a material named after him? Thank you, Ken Walters. It will be nice to be remembered.
If the general rheologist were asked, what do you immediately think about when Boger fluids are being discussed? I'm sure that many would point to a number of complex flows, particularly those involving contraction geometries. Indeed, David has already referred to the classic sequence of pictures demonstrating vortex enhancement in an axisymmetric contraction, and we show a later version of the same phenomenon published in 1986. We shall need to consider this and similar flows in a moment, but to set the scene, it is helpful to consider a number of simple rheometrical flows, which conveniently demonstrate what distinguishes Boger fluids from Newtonian fluids of comparable viscosity. Consider first a steady simple shear flow, with constant shear rate gamma dot. In this flow, the relevant stress distribution is described by three so-called viscometric functions. The viscosity eta is usually a strong function of gamma dot, with shear thinning by far the most common response for non-Newtonian elastic liquids. The normal stress differences are important manifestations of viscoelasticity. We have already referred to the fact that shear thinning is absent, or is at least insignificant, in the case of Boger fluids, whilst at the same time the first normal stress difference can be very high indeed. Recall that N1 is 0 for a Newtonian fluid. David has already indicated that for Boger fluids, so-called second-order behavior exists over a reasonable range of shear rates. That is, the shear stress is a linear function of shear rate, and the normal stress differences are quadratic functions of shear rate. As it happens, the second normal stress difference is usually very small for Boger fluids and is invariably ignored. At high shear rates, there is usually some slight shear thinning, with the viscosity falling from the 0 shear rate value to a value close to that of the solvent. This is accompanied by a first normal stress difference behavior, which is weaker than quadratic. You will notice that in the quadratic region, we have introduced a characteristic relaxation time constant lambda. However, from dynamic data, it soon became apparent that these liquids usually need more than one relaxation time. For example, some detailed work of David Boger and his team, published in 1991, indicates that the minimum number of time constants is likely to be at least 3. This will become important later when we consider constitutive models for this class of elastic liquid. The final rheometrical function we must refer to is the extensional viscosity, denoted by eta sub e. For a Newtonian liquid of viscosity eta, the extensional viscosity is simply 3 eta, a result first obtained by Troughton almost a century ago. For this reason, the ratio of extensional viscosity to shear viscosity is conveniently known as the Troughton ratio. For Boger fluids, the Troughton ratios can be very high indeed. This is a very important difference between Newtonian and Boger fluids. We show one extravagant example of what this can mean for Boger fluids. But let us concentrate on the axisymmetric contraction flows that first brought Boger fluids to our attention. In some ways, the classic set of still pictures of vortex enhancement we have already seen tell their own story. But there is no doubt that rheologists have enjoyed viewing and studying the associated videos. These were made by David Boger and his collaborators in the 70s and 80s. The film sequences are usually associated with increasing flow rates, other things being equal. We are viewing an early video produced in the late 70s. The contraction ratio is 7.67 to 1. Flow is from right to left, and the fluid is a polyacrylamide solution in a viscous solvent consisting of water and syrup. As the flow rate increases, we see typical vortex enhancement, followed by various unstable flow regimes, including rotating flow, helical flow, and other more bizarre instabilities. But let us pass on to later videos produced by the Australian group in the late 80s. Here, flow is from left to right, the contraction ratio is 4 to 1, and the fluid is another polyacrylamide-based Boger fluid. The change in flow structure with increasing flow rate is clearly evident. Interestingly, in this case, the corresponding still photographs are very attractive and revealing, and have become quite well known to computational rheologists. We now consider the same fluid in a lower contraction ratio geometry, 2 to 1 to be precise. In this sequence, we see definite evidence of a so-called lip vortex, which often becomes a dominant influence in the build-up to vortex enhancement. David Boger's experiments have shown that contraction ratio is not the only important variable. The contraction angle is also relevant. So we show a sequence for the same liquid with diminishing contraction angle. Flow conditions are very similar in each case, and we see the not unexpected disappearance of the vortex structure as the contraction geometry becomes less abrupt. Finally, we show two pictures which illustrate the importance of the sharpness of the corner in axisymmetric contractions. The conditions in both pictures are the same, except that the corner has been rounded in the right-hand picture. Clearly, this has a dramatic effect on the flow structure. Vortex enhancement in axisymmetric flows is invariably accompanied by a substantial increase in the pressure drop required to produce a given flow rate over that expected on the basis of shear viscosity alone. We show an example of this from some experiments carried out recently at the University of Wales. The comparison is for a Boger fluid and a Newtonian fluid with the same shear viscosity. We see plots of pressure drop versus flow rate for both liquids. Clearly, in the axisymmetric case, where vortex enhancement is in evidence, the flow rate for a fixed pressure drop is significantly lower in the case of the Boger fluid. Over the years, it has become evident that the flow of Boger fluids in planar contractions is qualitatively different from that in the axisymmetric case. Here, vortex enhancement is conspicuous by its absence, as the representative pictures demonstrate. When a pressure drop flow rate experiment is carried out in the planar case, we see that in this case, there is no measurable difference between the responses for Newtonian and Boger fluids of the same viscosity. The pressure drop flow rate response is usually studied through the so-called Couette correction. So rheologists often talk of the significant increases in the Couette correction for Boger fluids flowing in axisymmetric contractions. After the initial introduction of Boger fluids and the appearance of the classic set of contraction flow videos, it is not surprising that these fluids have also been investigated in other complex geometries. So we show pictures of flow over a two-dimensional slot, which demonstrate that, in these experiments at least, fluid inertia and viscoelasticity are opposing influences, in the sense that the resulting secondary flows in the hole have opposite asymmetries. The pictures on the left are for Newtonian fluids at 2 Reynolds numbers, while those on the right are for Boger fluids at comparable Reynolds numbers. In so-called combined mixing separating flow, where the arrows indicate the direction and strength of the flows in the various arms, Newtonian fluids permit easily generated symmetric pictures, with a strong indication of a preference for reversed flow around the obtrusions rather than unidirectional flow in the horizontal directions. In the corresponding experiments for Boger fluids, symmetry is elusive and difficult to generate. Also, there is now a strong preference for unidirectional flow, with a smaller component of reversed flow. Loosely, one might say that Boger fluids have an aversion to turning corners. This is better demonstrated in flow in a two-dimensional T-geometry. Here, fluid enters the left-hand arm and exits through the right-hand arm and also the vertical arm. The Newtonian fluid has no difficulty turning into the vertical arm. In contrast, the Boger fluid seems reluctant to do so, with a consequent massive overshoot before the fluid finally agrees to enter the vertical channel. As these provocative experimental results for Boger fluids began to appear in the literature, there was a natural attempt to simulate them theoretically and computationally using the techniques of computational rheology. Interestingly, a surge of interest in this field took place at about the same time the Boger fluid experiments began to be widely known, and the experimental results provided an obvious challenge for those who were attempting to adapt established CFD techniques to meet the new challenges provided by highly elastic liquids flowing in complex geometries. At that time, there were two main challenges. The first was to decide on an appropriate constitutive model for Boger fluids. The second was to choose an appropriate numerical technique in the computations. This is not the place to address the latter issue, but it is of interest to follow and explain perceived wisdom on the issue of an appropriate constitutive model for Boger fluids. For many years, an obvious choice met with almost universal acceptance. The so-called Oldroyd B model seemed to have a relative simplicity and possessed some attractive features so far as rheometrical prediction was concerned. In a steady simple shear flow, the Oldroyd B model predicts a constant viscosity and a quadratic dependence of first normal stress difference on shear rate. The second normal stress difference is zero. In a uniaxial extensional flow, the model predicts an extensional viscosity which becomes infinite at a finite value of strain rate, which seemed high enough to satisfy even the most demanding theoretician. Over the last 25 years or so, there has been impressive progress in computational rheology, and numerical simulations for the Oldroyd B model are now able to predict the onset of vortex enhancement, the appearance of lip vortices, the provocative differences between planar and axisymmetric contraction flows, and many of the other flow characteristics we described earlier. What we are seeing here is a representative collection of such simulations, the first being a motion blur animation linked to a Swansea hybrid finite volume finite element scheme. This is followed by some Lagrangian finite volume simulations from the University of Wales, Aberystwyth. The third sequence is a well-known example of the extensive finite element simulations of the Belgian group of Marcel Crochet from the mid-80s. Finally, we see some early finite difference simulations for mixing separating flow. Unfortunately, at the present time, all simulations are singularly unable to predict the very large increases in the Couette correction that accompany vortex enhancement in the axisymmetric contraction flow experiments, something David Boger has already referred to. The inevitable conclusion has been that the Oldroyd B model is too simple. We have already referred to the fact that, whereas the Oldroyd B model has only two time constants, at least three are thought to be needed to represent the dynamic data obtained from small amplitude oscillatory shear experiments. But this is far from being the only or even the major reason for the disagreement between pressure drop predictions and experimental results. The situation is nowhere near being resolved. So much progress, yes, but some challenging unanswered questions remain. Perhaps by the time you view this presentation, progress will have been made on this outstanding problem.